When you go to a doctor, like say you think you broke your arm, they don't really have to guess,
Right, they just send you down the hall.
Exactly. You put your arm in that massive machine, and the X-ray spits out this crisp, jagged white line on a black background.
And the doctor just points right at it.
Yeah, they say, there's the break. It's totally binary. It's definitive. You throw a cast on it and go home.
It's incredibly comforting, honestly. I mean, we have this deeply ingrained human desire for things to just be visible.
Oh, totally.
We want things categorized. We want a singular cause. The trauma caused the break. End of story.
But then you step out of the hospital.
Right.
And you step into the real world. You step into the world of human behavior or global economics or public policy.
Which is a lot messier than a broken bone.
Way messier.
Yeah.
But people still make these massive, sweeping claims all the time. Like you'll hear someone on the news declare, raising the minimum wage kills jobs.
Or, spending more money on a political campaign guarantees a win.
Right. Or every year of college you finish adds exactly this much money to your lifetime earnings.
And we tend to nod along because, well, those statements sound really authoritative.
They sound like they're backed by that same kind of diagnostic certainty as the X-ray.
Exactly.
But here's the secret for you listening today. The economic X-ray machine is fundamentally broken. Or rather, it doesn't even exist.
Yeah, how do you take an X-ray of an entire economy?
You can't. How do you prove, beyond a shadow of a doubt, that pulling one single lever actually caused a specific outcome, especially in a world where, 8 billion other levers are being pulled at the exact same time?
It's absolute chaos.
It is. Untangling the true cause and effect from just the deafening noise of everyday life seems impossible.
It is basically the defining challenge of the social sciences. I mean, when a doctor looks at a bone, they're looking at it in a vacuum.
Right.
But when an economist looks at a market or a sociologist looks at a community, they can't isolate a person in a petri dish. Humans are messy, unpredictable, and just infinitely complex.
Which brings us to our mission for you today. We're going to look at how the professionals actually attempt to fix that broken diagnostic machine.
We are taking a deep dive into the absolute bedrock of data analysis.
Yep, using excerpts from Chapter 2 of Jeffrey Wooldridge's highly regarded textbook, Introductory Econometrics.
It's a text that literally sits on the shelf of almost every serious data scientist and economist working today.
It really does.
It provides the mechanical blueprint for how we translate all that chaotic reality of human behavior into mathematics, and then crucially, how we translate those mathematical results back into something we can actually use.
Okay, let's unpack this. If you ever glanced at an econometrics textbook, your first instinct might be to just run away.
It is a wall of Greek letters.
A total wall. Greek letters, college algebra, terrifying statistical formulas. But we are not doing a dry math lecture today.
No, absolutely not.
We're going to translate this into plain English. Think of today as unlocking a secret decoder ring for reality.
I like that.
We want to give you a shortcut to understanding a concept called the simple linear regression model.
The name itself sounds a bit intimidating.
A little bit.
But the core philosophy behind it is actually quite intuitive. It's really just about drawing a line through the chaos.
So let's start with the absolute foundation, the anatomy of a relationship. The text introduces us to the fundamental equation of this entire field.
The big one.
Now, I'm going to read the letters, but we're going to immediately strip them of their mathematical armor. Okay.
Yeah.
The equation is y equals beta 0 plus beta 1 times x plus u.
This is the starting point for almost all applied econometrics.
Just that little string of letters.
Yeah. It looks like the equation for a straight line that you might remember from middle school math, but the philosophy it represents is profound. It's a way of formally stating how we believe the world actually operates.
Let's define the cast of characters here. We have y and we have x. These are our variables, right?
Right. These are the things we can actually go out into the world and observe.
We can measure them, put them into a spreadsheet. The text calls Ani the dependent variable or the explained variable.
I actually prefer the term explained variable. It's the phenomenon you care about. It's the outcome you're trying to understand.
Okay, so if I'm an agricultural researcher, my y might be like the total yield of my soybean crop at the end of the season.
Exactly. And your x is the independent variable or the explanatory variable.
The thing doing the explaining.
Right. The lever you suspect is driving the outcome. So in your soybean example, your x might be the exact pounds of fertilizer you apply to the field.
Because I want to explain the crop yield, the y, in terms of the fertilizer, the x.
Precisely. Or, moving away from plants and into people, the text uses a classic labor economics example.
Oh, the wage one.
Yeah. Our explained variable, our y, is a person's hourly wage, and the lever we think affects it, our x, is their years of formal education.
Those are perfect examples. You have an outcome, and you have a single factor you believe influences that outcome.
But here is where the math really collides with reality.
Yeah, because if the universe were just a perfect deterministic machine, the equation would just be y and x.
There wouldn't be anything else.
Right. I put in exactly 1 pound of fertilizer, and the machine spits out exactly 10 extra soybeans. Every single time.
But we know that's not how reality works. I mean, if you put a pound of fertilizer on a patch of dirt during a severe drought,
I get nothing. Dead plants.
Exactly. And that reality introduces the most crucial, the most mysterious, and frankly, the most philosophically fascinating part of this entire equation.
The U.
The U.
Yes, the U. The text officially calls it the error term, or the disturbance. But I just love how it's described conceptually. It's essentially an abbreviation for unobserved.
What's fascinating here is that the U is the mathematical representation of our own ignorance.
A literal bucket for our ignorance.
That is exactly what it is.
We write an equation that confidently claims we know what's happening between y and x, and then we just like to tack on a plus u at the very end to catch literally everything else in the universe.
It is an act of profound mathematical humility.
That's a great way to put it.
A simple regression analysis treats every single factor that affects y other than the one specific x we chose to measure as unobserved.
Everything we can't measure.
Everything we don't have the budget to measure and everything we don't even know exists. It all gets thrown into that U bucket.
Let's make this really concrete. Back to the farm. My y is the soybean crop yield. My x is the fertilizer. What exactly is swimming around inside that U bucket?
Oh, it's a crowded bucket. It contains the exact mineral composition of the soil in that specific field.
Okay.
It contains the precise amount of rainfall that season, the hours of direct sunlight, the presence of a specific type of beetle that eats soybean leaves.
The DNA of the seeds.
Yes, the microscopic genetic variations in the seeds you planted, unless you have a spreadsheet column meticulously tracking the daily beetle population and the soil pH.
Which nobody does.
Right. All of those incredibly important factors are just lumped together as up.
And what about the wage example? If y is hourly wage and x is years of education, man, the U bucket, there must be the size of a galaxy.
It really is. I mean, think about it. What determines a person's wage besides their diploma?
Their innate intelligence.
Your work ethic. How many years they've been at that specific company.
Whether they're good at negotiating.
The wealth of their parents. Pure, unadulterated luck. Like, did they happen to interview on a day when the hiring manager was just in a great mood?
Yeah.
All of that is you.
You know, I like to think of this equation like baking.
Okay, I like baking.
So I am obsessively trying to figure out how to bake the perfect cake.
Yeah.
The final objective taste of that cake. Let's say we have a machine that scores taste from 1 to 10. That's my y.
The outcome.
The amount of sugar I pour into the bowl is my x. I can measure the sugar down to the gram. But the U is the ambient humidity in my kitchen that afternoon.
Oh, wow.
It's the fact that my particular oven runs a little hot in the back left corner. It's whether the eggs I bought were laid 3 days ago or 12 days ago.
It's how vigorously you whisked the batter.
Exactly. It's all the invisible stuff that makes baking an art instead of just a rigid chemical formula.
That is a brilliant way to conceptualize it. Because the challenge of econometrics, the whole reason this field even exists, is that we are trying to figure out the true effect of the sugar.
The pure effect of X.
Yes. While the humidity and the oven temperature and the egg freshness are constantly changing in the background and messing with our final cake.
Which brings us to the actual mechanics of the equation. We know Y, X, and U. But what about those Greek letters, the beta 0 and beta 1? The text calls these the parameters.
These are the theoretical true numbers of the universe that we were trying to discover.
It's hidden code.
Right. Beta 0 is the intercept. In the language of a graph, it's where the line crosses the vertical axis. It's the expected value of your outcome, y, if your lever x is completely set to 0.
So the base taste of the cake with literally 0 sugar, or the crop yield with 0 fertilizer.
Exactly. It provides a baseline. The real star of the show, the number that economists spend their entire careers trying to pin down, is beta 1. This is the slope parameter. It measures the exact pure effect of x on y. It basically tells us, if we increase x by exactly 1 unit, how much does y change?
If I add 1 more cup of sugar, How many points does my cake taste score go up?
Or if I stay in school for one more year, exactly how many dollars get added to my hourly wage?
Exactly. But the text highlights a massive foundational caveat here. Beta 1 only measures the true effect of X on Y if all the other factors inside the U bucket remain completely unchanged.
The famous ceteris paribus assumption.
Yes, all else being equal.
Mathematically, it states that the change in y equals beta 1 times the change in x, but only if the change in is absolutely 0.
Okay, hold on. This is where the whole thing starts to feel like a parlor trick.
Why is that?
Because we just spent all this time establishing that the U bucket is full of chaotic, constantly changing real-world factors. The weather changes. People's work ethic changes.
They do.
How can we possibly calculate the true effect of the fertilizer if we have to magically pretend the rainfall and the bugs just freeze in place? I can't control the weather outside my kitchen when I'm baking?
You've hit on the central paradox of observational data.
It seems impossible.
In a perfectly controlled laboratory, a chemist can freeze the U factors. They can control the temperature, the pressure, the humidity.
Right.
But an economist cannot freeze the world. We can't put a worker in a vacuum to see what their wage would be.
So if we can't physically freeze the U bucket, it seems like we are completely stuck. Like, how can we possibly draw a causal conclusion? How can anyone confidently say more education causes higher wages if they are willfully ignoring a universe of unmeasured variables that are constantly shifting?
We aren't entirely stuck, but to get out of this trap, the math demands that we make a very specific and incredibly powerful assumption.
About what?
About how our observable lever, X, relates to our unobservable bucket of ignorance, U. We have to bridge the gap between what we know and what we don't know.
And this transition brings us to what I consider the absolute holy grail of this entire deep dive.
Oh, the big one.
It's a concept that sounds like a meditation mantra, the zero conditional mean assumption.
It really is the tightrope walk of all econometric analysis. If this assumption holds, we can actually uncover truth.
And if it fails?
Our simple linear regression completely collapses. It becomes nothing more than a neat line drawn through a pile of meaningless dots.
Okay, let's break down how the text builds up to this assumption, because it does it in steps. First, it tells us that we can just make a basic blanket assumption that the average value of everything in the U bucket across the entire population is 0.
The expected value of U is 0.
Yeah. Let me just say, that sounds absurd on its face. How can ignorance average out to 0?
It sounds absurd until you realize it's actually just a clever, harmless mathematical trick.
A trick.
Yeah, it doesn't cost us anything to assume this because of how we defined our equation. Think about the unobserved factors affecting your soybean yield, like the underlying quality of the soil.
Okay. Some soil is incredibly rich, dark loam. Some of it is dry, sandy garbage.
Right. So we simply normalize our definition of soil quality. We look at all the farmland in our entire population, and we define the exact average soil quality as 0.
Oh, I see.
Therefore, any plot of land with better than average soil gets a positive number in the U bucket. Any plot with worse than average soil gets a negative number.
And by definition, if you add all the positives and negatives together, the average of the whole population is 0.
Exactly.
It's like saying, let's define sea level as 0 altitude. It doesn't mean the ocean doesn't exist, and it doesn't mean mountains aren't tall. It just gives us an arbitrary baseline to measure from.
That's a perfect analogy. And because our equation has that intercept term beta 0, the intercept acts like a sponge.
That's a sponge.
Yeah, if the true average of the unobserved factors isn't actually 0, the intercept just absorbs that difference. The intercept shifts up or down to account for the baseline. So assuming the average of U is 0 for the whole population is a trivial assumption. It doesn't restrict our model at all.
But the text is very quick to point out that this trivial assumption isn't enough to save us. Knowing that the overall average of our ignorance is 0 tells us absolutely nothing about how that ignorance interacts with the thing we are actually trying to measure.
Right. The relationship between U and X is the battlefield. That is where causality is won or lost.
Let's visualize why. If the unobserved things in the background are moving in tandem with the lever we are pulling, we are completely blind.
We are.
If every time I add an extra cup of sugar to my cake batter, the humidity in my kitchen simultaneously spikes by 20% and my cake comes out ruined, I don't know who to blame.
Was it the sugar or the humidity?
Exactly. They are confounded.
Confounding variables are the bane of statistics. So we need to mathematically express the idea that our lever X and our background noise, U, do not move together.
Right.
A natural first step, which most people who have taken a basic stats class might think of, is correlation. We could just assume that U and X are completely uncorrelated.
I remember correlation. It's like watching two dancers. If they always step to the left at the exact same time, they're positively correlated.
Right.
If one steps left while the other steps right, they are negatively correlated. And if one is doing the waltz and the other is breakdancing completely randomly, they are uncorrelated.
That's a really great visual. But the text warns us that simply assuming zero correlation isn't strong enough.
It isn't.
No, it's a quirk of statistics, but correlation only measures linear dependence.
Oh.
It's entirely possible for two variables to have zero linear correlation, meaning you can't draw a straight line showing how they move together, but they might be deeply connected in a curved, nonlinear way.
Like what?
For instance, you could be completely uncorrelated with X, but perfectly correlated with X squared.
So the breakdancer and the waltz dancer might look totally uncoordinated, but they are actually listening to the exact same complex rhythm, just expressing it differently.
Exactly.
If we only look for a simple, linear, step-by-step connection, we'll totally miss the underlying relationship.
Precisely. For our simple regression model to truly isolate the effect of X, we need a much stronger wall between our lever and our ignorance. We need something called conditional independence.
Conditional independent.
We need to look at the expected value of U, given a specific value of X.
And here we arrive at the mantra, the zero conditional mean. Mathematically, it's written as the expected value of U, vertical bar X, equals the expected value of U.
The vertical bar means given or conditional upon.
Let's translate that math into a physical thought experiment. Imagine you have the entire working population of a country. Millions of people.
Okay.
You want to understand the relationship between their years of education, X, and their unobserved innate ability, which lives in the U bucket.
So I'm picturing a giant convention center with millions of workers milling around.
Right. Now, slice that population up based entirely on their education level. Take every single person who has exactly 8 years of education, they finished middle school, and stopped and put them in room A.
Got it.
Then, take every single person who has exactly 16 years of education, they finished a 4-year college degree, and put them in room B.
So the rooms are sliced by X.
Exactly. Now, the zero conditional mean assumption requires that if you could somehow magically scan everyone's brain in room A and calculate their average innate ability, and then go to room B, magically scan their brains, and calculate their average innate ability.
Yes.
Those two averages must be absolutely exactly identical.
This raises an important question, and you've just put your finger on the exact reason why social sciences are so difficult.
Wait, I have to stop you. I have to push back on this, because this is where the math seems to completely detach from reality.
How so?
You are telling me that the foundation of this economic model requires us to assume that the average innate natural genius of a room full of middle school dropouts is identical to the average innate genius of a room full of college graduates. But that defies common sense. People who are naturally gifted at taking tests, people who have high innate cognitive ability, generally choose to stay in school longer because school rewards them. It's easier for them.
It is.
So room B, the college graduates, will almost certainly have a higher average innate ability than room A.
You are absolutely right. And what you've just described is a scenario where the zero conditional mean assumption completely and catastrophically failed.
Gets failed.
Yes. If higher innate ability leads people to get more education, then the expected value of our unobserved factor U is not constant across the different slices of X.
As X goes up, the average of U goes up with it.
They are inextricably linked.
And if the assumption fails, what happens to our beautiful equation?
The equation betrays us. It fails to show true causality. If the assumption fails, the unobserved factors leak into our observable measurements.
Oh, wow.
When we run our data through the computer and it tells us that a person with 16 years of education makes $5 an hour more than a person with 8 years of education, we are completely blind as to why.
We don't know if that $5 bump is the true, pure effect of what they learned in those extra 8 years of school, the beta 1 effect, or if the bump is just because the people who happen to have 16 years of education also happen to be naturally smarter and harder working.
Right, and it's their innate ability, the U effect, that the employer is actually paying for.
We call this omitted variable bias, right? Or selection bias.
Exactly. The math will happily draw a crisp, clean line through the data. It will give you a specific number for the wage increase, but the math cannot tell you if the education caused the wage increase in a true ceteris paribus, all else being equal sense.
That is a staggering limitation. It means that simple linear regression isn't a magic wand that reveals the hidden gears of the
Not
universe.
at all.
It's an incredibly fragile tool that only works if the environment is perfectly sterile. If your liver is tangled up with your background noise, the tool breaks.
It really highlights the limits of the math, but it also clarifies exactly what we need to look for when evaluating a study. We have to ask, in this specific scenario, is it reasonable to assume the lever was pulled independently of the background noise?
Let's go back to the farmer.
Okay.
Suppose the farmer has 10 plots of land. He knows that plot number 1 has terrible, sandy soil, so he intentionally dumps a massive amount of extra fertilizer on it to compensate.
Sensible farming.
Right. And he knows plot 10 has rich, dark soil, so he uses almost no fertilizer there.
Oh, wow. In that case, the fertilizer is being directly determined by the soil quality.
The farmer's own brain is the confounding variable.
He is ensuring that the average soil quality for the high fertilizer plots is actually worse than the average soil quality for the low fertilizer plots.
Exactly. The zero conditional mean assumption fails because of the farmer's behavior.
Right.
If you just looked at the raw data at the end of the year, it might look like fertilizer actively destroys crops because the plots with the most fertilizer had the lowest yields.
But that's a completely backwards causal conclusion.
So how do you fix it? How do you make the assumption hold?
The gold standard is a randomized controlled trial. If the farmer wants to know the true effect of the fertilizer, he can't use his judgment. He has to assign the fertilizer amounts completely at random.
Like, he rolls a pair of dice for each plot.
Yeah, whatever number comes up is how many pounds of fertilizer he uses.
If he does that, then the decision of how much fertilizer to use is completely decoupled from the soil quality. It's just random chance.
Yes. And because it's random chance, if we slice the plots up by how much fertilizer they received, the average soil quality across all those different slices should, theoretically, be identical.
The zero conditional mean assumption holds. The background noise is balanced out.
Exactly.
Okay, so let's assume we actually achieve this miracle. Let's assume we find a scenario, or we run a perfectly randomized experiment where the zero conditional mean holds true. The U bucket is perfectly balanced across all our slices of X. What do we get for our trouble?
We get something statistically beautiful. We get the population regression function, or the PRF.
All right, I remember this from the text. The PRF drops the U entirely. It states that the expected value of Y given X equals beta 0 plus beta 1X. It looks like the cleanest, simplest equation in the world.
It is elegant. Because we've ensured that the expected value of the noise is 0 across every slice of X, we can simply drop the U when we are talking about averages.
We can confidently declare that the expected, or average, value of our outcome Y for any specific level of X is a pure straight-line function of X.
We have successfully split reality into two distinct parts.
The systematic part, which is the line itself, beta 0 plus beta 1X,
Right.
that's the part completely and causally explained by our lever.
Right.
And the unsystematic part, the U, which is just the random, unpredictable static hovering above and below that line.
And understanding the difference between the expected average and the individual reality is crucial. The text uses a fantastic example to drive this home regarding university grades.
Oh, yeah.
Suppose we have a flawless model that predicts a student's university GPA based solely on their high school GPA. The systematic part of the equation, the PRF, is expected university GPA equals 1.5 plus 0.5 times high school GPA.
Okay, let's plug a number in. Let's take a group of students who all achieved a very respectable 3.6 GPA in high school. That's our X.
Okay.
We plug 3.6 into the equation. 1.5 plus half of 3.6. Half of 3.6 is 1.8. So 1.5 plus 1.8 equals 3.3. The math says their expected university GPA is 3.3.
Now, here is the critical point of interpretation. Does this mean that if you find a specific student named Sarah who had a 3.6 in high school, the model guarantees she will graduate university with exactly a 3.3?
Obviously not. That would mean we eliminated free will. It would mean the U bucket is completely empty, which we know isn't true.
Exactly. Sarah's an individual. She has her own personal U bucket. Maybe she gets to university and discovers she hates her major, gets distracted by extracurriculars, and graduates with a 2.5.
Her personal U was heavily negative.
Yes. And another student with a 3.6 high school GPA, let's call him David, might find his absolute passion in a university lab, study relentlessly, and graduate with a perfect 4.0.
His personal you was highly positive.
Exactly.
The line doesn't dictate the destiny of the individual.
No, the population regression function only describes the center of gravity. It tells us that if you take all 10,000 students who had a 3.6 in high school and you average their final university GPAs together,
The positive surprises and the negative disasters in their individual U buckets will cancel each other out.
and the group average will land squarely on 3.3.
It's like predicting the weather. You can't tell me exactly where one specific raindrop will land on my driveway, but you can tell me with high confidence that my entire driveway will get exactly 1 inch of water.
A perfect analogy. The PRF predicts the total rainfall. The U is the trajectory of the individual drop.
Okay, so we have mapped out the theoretical universe. We have our perfectly balanced equations, our population parameters, our pristine ceteris paribus assumptions.
The theory is solid.
But there's a massive problem. We don't live in a theoretical universe. We don't have omniscient access to every single soybean plant on Earth, or the high school transcripts of every human being who has ever lived.
Right, we only ever have fragments.
We have samples, messy, limited, finite spreadsheets of data.
And this is where the discipline transitions from the pure theory of probability into the applied science of statistics. We have to build a bridge from the sample we have in our hands to the population we want to understand.
We need estimators. We have to move from the theoretical population parameters, the pure beta 0 and beta 1, to our sample estimates.
Right.
The text denotes these estimates by putting little hats on the Greek letters. Beta 0 with a hat and beta 1 with a hat. I always like the hats. Makes them look like they're going to work.
The hats are vital notation. A parameter without a hat is a fixed, unchangeable truth of the universe.
A parameter with a hat.
Is a guess based on the data you happen to have in your spreadsheet today. If you collect a new sample tomorrow, the number under the hat will change.
The text calls the process of finding these estimates the birth of ordinary least squares, or OLS. How does OLS actually calculate these hat numbers? The text mentions a phrase that sounds incredibly profound. The method of moments.
The method of moments is one of the most elegant conceptual leaps in statistics. Let's trace the logic. We started with two core theoretical assumptions about our population.
Okay.
First, that the average of the error term, the U, is 0. Second, that the error term has 0 correlation with our lever, x. Those are the rules of the universe we are trying to model.
Right. The baseline is 0, and the background noise doesn't dance with the lever.
So the method of moments simply says, let's take those theoretical rules of the universe and use them as a cookie cutter on our raw data. We force our sample data to obey the exact same rules we assume the population obeys.
We make the sample mimic the theory.
Exactly. We write down an equation that literally forces the average of the calculated errors in our sample to be exactly 0. And we write down a second equation that forces the correlation between our sample's errors and our sample's x values to be exactly 0.
We now have two equations, and we have two unknowns, our beta 0 hat and beta 1 hat.
And anyone who survived high school algebra knows that if you have two linear equations and two unknowns, you can solve for the unknowns. You just plug the data in and turn the crank.
It is mathematically guaranteed to give you an answer. The text spends a page walking through the algebraic rearrangement, using summation signs to isolate the hats.
It's a rigorous proof, yes.
But you don't need to memorize the derivation to understand what it's physically doing. It's much easier to understand the physical intuition behind OLS. It is fundamentally an exercise in minimizing mistakes.
Yes, let's visualize this because I think seeing the geometry of it makes it really click. Let's say you and I conduct a survey. We go out and ask 15 random families 2 questions. What is your annual income? And how much money do you have in savings? We take those 15 pairs of numbers and we plot them on a large graph on a whiteboard. Income is the horizontal axis, our x. Savings is the vertical axis, our y.
When you step back, you see a scattered cloud of 15 dots. Because families with higher incomes generally have more savings, the cloud of dots has a rough, upward sloping trend from bottom left to top right.
But it's not a perfect line, it's messy. Some high-income families spend everything they make. Some low-income families are incredibly frugal.
Our goal is to draw a single, perfectly straight line through that messy cloud of dots that best captures the underlying trend. We want the line of best fit.
Now imagine drawing a random line through the cloud. For every single family, let's call a specific family with income in SCA, our line is going to make a prediction about what their savings should be.
We call this prediction the fitted value. The text uses I hat sub I.
Right. It's the exact point on our drawn line directly above or below the family's true income level. The
Right.
formula is y hat sub I equals beta 0 hat plus beta 1 hat times 11.
It's what the model thinks they should have saved. But the real family doesn't usually sit perfectly on our line. Their actual real-world savings in the bank is y.
Right.
The physical distance on the whiteboard between where the dot actually is and where our line predicts it should be is a measure of how wrong our line is for that specific family.
We call that specific distance the residual. The text makes a very careful distinction here that confuses a lot of students. We have to distinguish between the unobserved error, the E in the invisible population model, and the calculated residual, the U hat sub I, from our sample line.
So U without a hat is the true unknowable mystery of the universe. The U with a hat is just the mathematical mistake our specific line made.
Exactly. The residual is a concrete, measurable number. It is simply U hat sub I equals U minus Y hat sub I, the actual truth minus our prediction.
Got it.
If a family saved $10,000 more than our line predicted, their residual is a positive $10,000. If they saved $5,000 less than we predicted, their residual is a negative $5,000.
So we have 15 families on the board. We draw a line. We now have 15 residuals, 15 measurements of how wrong we are. Obviously, we want to find the one magic line that makes our total wrongness as small as possible.
The core mechanism of ordinary least squares is choosing the intercept and slope that minimizes the sum of squared residuals, the SSR.
This is where the name comes from, ordinary least squares. We literally take every single residual, we square it, and we add them all up into one giant sum.
The OLS machine iterates through every possible angle and height for the line until it finds the absolute mathematical minimum for that sum.
I have a physical analogy for this that always helped me picture the map.
Oh, let's hear it.
Imagine that whiteboard again. The scatter plot of 15 dots is drawn on a thick piece of wood. Now you take a hammer and you pound a little steel nail directly into each of the 15 dots.
Okay, 15 nails.
Next, you take a stiff, rigid metal wire. This wire is going to be our regression line. Finally, you take 15 identical rubber bands and you hook one end of the rubber band to the metal wire and you stretch the other end down or up to hook onto a nail.
That is a phenomenal visualization. The stretched rubber bands perfectly represent the residuals, the vertical tension between the rigid prediction line, and the messy reality of the data points.
Exactly. Now, you are holding the wire. What happens when you let go?
It snaps.
The wire is instantly subjected to physical forces. The nails above the wire are pulling it up. The nails below the wire are pulling it down. The wire will snap, shift, and angle itself, reacting to the pull of all 15 rubber bands simultaneously.
Right.
Eventually, very quickly, the wire will settle into an equilibrium. It will find a resting place where the total combined tension from all the rubber bands pulling in opposite directions is perfectly balanced and minimized.
That resting place, that precise physical angle and height where the tension is zeroed out, is exactly what the OLS formulas are calculating. The physical tension in your analogy is the exact mathematical equivalent of minimizing the sum of squared residuals.
But the rubber band analogy highlights a mathematical quirk that the text addresses, and that I've honestly always wondered about.
What's that?
Why squares? Names ordinary least squares. Why are we minimizing the sum of the squared residuals? Why not just measure the raw physical distance, the absolute value of the residual, and minimize that?
It's a very common question.
Because squaring things seems like we're just inflating the numbers for no reason. If a point is 5 units off the line, squaring it makes it 25. If it's 10 units off, it becomes 100. It blows the math up.
There are two primary reasons why OLS uses squares. The first is pure pragmatic calculus. When you want to find the absolute minimum of a mathematical function, you use calculus. You take the derivative of the function and find where it equals 0.
Finding the bottom of the bowl.
Exactly. A function based on squared values forms a beautiful, smooth, U-shaped parabola. It's like a smooth bowl. The calculus required to find the exact bottom of a smooth bowl is trivial. It results in simple, elegant, linear algebraic formulas that a computer can solve in a microsecond.
And what if we use the absolute value?
An absolute value function doesn't form a smooth bowl. It forms a sharp, jagged V shape. A V has a sharp corner at the bottom. In calculus, a sharp corner is a nightmare because it is not differentiable.
Oh, right.
You can't just run a simple formula to find the bottom. You have to use complex, iterative, computationally expensive numerical algorithms to hunt for it. By using squares, we get neat, closed-form formulas for our estimators that we can calculate instantly.
So the math is just vastly easier. The text shows the formula for the slope, beta 1 hat, And it really is clean. It's just the sample covariance between x and y divided by the sample variance of x. It's a simple fraction.
Yes. But there's a second conceptual reason we use squares, beyond just mathematical convenience. Squaring the residuals fundamentally changes how the line behaves. It heavily penalizes large errors compared to small ones.
Because of the exponential growth.
Exactly. As you noted, an error of 2 becomes a penalty of 4. An error of 10 becomes a penalty of 100. OLS really, really does not like it when the line is very far away from a data point.
It panics.
Yeah, the mathematical penalty is so severe that the line will aggressively pull itself toward outliers, those extreme data points sitting way out on the edge of the graph, just to avoid that massive squared penalty.
Let's go back to the rubber bands. If I take one of those nails and I move it 3 feet up the board, the rubber band is going to be stretched so tight it's near breaking.
Right.
It's going to exert massive tension on the wire, pulling the whole wire upwards away from the other 14 dots just to relieve the tension of that one extreme outlier.
Which can be a powerful feature or a fatal flaw, depending entirely on your data. If that outlier is a genuine, important phenomenon, say, an incredibly rare but real economic event, OLS ensures it is heavily weighted.
But what if it's a mistake?
If that outlier is just a typo in your spreadsheet, like someone accidentally added an extra 0 to their income, OLS will completely distort the line of best fit to accommodate a mistake.
So OLS is elegant, but it is highly sensitive. It trusts the data implicitly. Assuming your data is solid, OLS provides estimators that are considered consistent and unbiased.
Provided the foundational assumptions we discussed earlier hold true.
Right. Always back to the assumptions. Okay, so we have the mechanical blueprint of the OLS machine. We know how it turns messy dots into a clean line. Now, what happens when we feed actual complex human behavior into this mathematical machine?
That's where it gets real.
The text doesn't just leave us with theory. It gives us 3 fascinating real-world data sets to play with. Let's look at how we apply this.
These empirical examples are crucial. They bridge the gap between abstract algebra and economic reality. They show us how to interpret the numbers once the computer spits them out, and more importantly, they highlight the strict limitations of a simple linear model.
The first example looks at corporate America. We want to know the relationship between a CEO's salary and the performance of their company, specifically the company's return on equity, or ROE. The text uses a data set from 1990 featuring 209 CEOs. Our outcome, Y, is the CEO's salary measured in thousands of dollars. Our lever, X, is the company's ROE measured as a percentage. The computer crunches the numbers and estimates this equation. Expected salary equals 963.191 plus 18.501 times rho.
Let's translate that equation into English. First, the intercept, beta 0 hat, is 963.191. Because the y variable is measured in thousands, we have to multiply that by 1,000.
$963,191.
Exactly. That means when the return on equity, the X, is exactly 0, the model predicts the CEO's baseline salary will be $963,191.
Almost $1 million a year for generating literally zero return for the shareholders. It's good work if you can get it.
It speaks to the baseline compensation in that era, but the dynamic part is the slope, beta 1 hat, which is 18.501. This number tells us the marginal effect.
Right.
It means that for every 1 percentage point increase in ROE, the predicted average salary increases by $18,501,000, or roughly $18,500.
So if a CEO manages to boost their company's ROE from 10% to 11%, the model predicts they get rewarded with an $18,500 raise.
On average, across the population of CEOs, yes. And we can use this estimated equation to predict specific scenarios. If a company is performing exceptionally well and has an ROE of 30%, we simply plug 30 into the X spot. 963.191 plus 18.501 times 30 equals 1,518.221.
Wow.
The predicted average salary for CEOs at companies with 30% ROE is roughly $1.5 million.
But again, the text throws up a massive caution flag here. This is just the line of best fit, is the center of gravity. It does not mean that if we find a specific CEO named Bob, whose company has an ROE of 30%, Bob's W-2 is guaranteed to say exactly $1,518,221.
Absolutely not. Bob is an individual. We have to remember the U-bucket. The unobserved factors for a CEO are immense.
Oh, yeah.
Bob might have 20 years of tenure at the company, elevating his pay. Or maybe Bob is the founder's nephew. Or maybe Bob's company is in a booming tech sector, while another CEO with a 30% ROE is in a dying manufacturing sector.
So Bob's actual salary could be $3 million, or it could be $500,000. He will likely be way off the line. The equation only gives us the predicted average for that specific bracket of performance.
The line is the forest. The dots are the trees. Let's look at the second example. This returns to the labor economics question. Wage versus education.
Okay, my favorite.
The data set is 526 people in the workforce back in 1976. Our Y is hourly wage in dollars. Our X is years of formal education. The OLS machine digests the data and spits out this equation. Wage equals negative 0.90 plus 0.54 times a joke.
Here's where it gets really interesting. Look closely at that intercept. Negative 0.90.
Yeah.
I stared at that number for a while. If you have 0 years of education, you plug 0 into the X. The math says your expected hourly wage is negative 90 cents. You literally have to pay your boss 90 cents an hour for the privilege of working the cash register. That is biologically and legally impossible. It's absurd.
It is a complete absurdity. And the text doesn't hide it. It highlights it specifically to teach a vital lesson about the limitations of linear models. The math isn't broken, but its application has hit a wall.
Why is the intercept negative then?
You have to look at the underlying sample. Out of the 526 people in that 1976 data set, only 18 individuals had less than 8 years of education. The vast majority of the data is clustered between 8 years middle school and 16 years college.
The OLS wire is balancing itself against a thick cluster of nails sitting between 8 and 16 on the horizontal axis.
Exactly. The model is drawing a line of best fit through that specific local cluster. The linear model is fundamentally a local approximation. It works remarkably well within the dense range of the data it was trained on.
But if you take that rigid straight line and you blindly follow its trajectory all the way back down to the 0 mark on the axis,
Right.
an area where there's almost no actual data to guide it, it crashes straight through the floor of reality and into negative numbers.
It's like taking a map of downtown Chicago, noting that the streets are a grid, and then extrapolating that if you drive straight west for 1,000 miles, you'll still be on a paved grid street. Eventually, you hit the Rocky Mountains. The local map fails.
A perfect metaphor. It demonstrates the profound danger of extrapolating data beyond the boundaries of your sample. You cannot ask the math to predict a reality it has never seen.
But the slope is still useful, right? The 0.54, because that's measuring the trend inside the cluster?
Yes, the slope remains highly informative. Within the bulk of the data, the slope tells us that 1 additional year of education is associated with a 54-cent increase in the hourly wage. So, graduating with a 4-year college degree instead of stopping at high school predicts a $2.16 bump per hour in 1976 dollars.
Okay, let's hit the third empirical example. This one goes into political science. Voting and campaign spending. The data set is 173 congressional races in 1988 where there was a Democrat running against a Republican, candidate A and candidate B.
All right.
Our Y is candidate A's share of the total vote, a percentage. Our X is candidate A's share of the total campaign spending, also a percentage. The model estimates. Vote A equals 26.81 plus 0.464 times share A.
Let's interpret the slope first. 0.464. This means that if candidate A's share of the total spending goes up by 1 full percentage point, their share of the final vote is predicted to go up by roughly 0.46 percentage points, almost 0.5%.
So if they match their opponent perfectly and spend exactly 50% of the money, we plug 50 into the X. 26.81 plus 0.464 times 50 equals 50.01. Wow, it's almost perfectly symmetrical. Half the money buys exactly half the votes.
It is a very striking correlation. The data clearly shows that money and votes move together. But the text inserts a massive flashing caution sign here. It explicitly states it is not clear if this is a causal effect or not.
Because of our old nemesis, the U bucket.
Exactly. This raises an incredibly important question about reality versus mathematics. The math shows a line. But does the money cause the votes, or do the votes cause the money? Think about what is sitting unobserved in the U bucket in a political race.
The actual quality of the candidate, their charisma, their debate skills, their alignment with the district's values.
Precisely. A very charismatic, popular candidate will naturally attract more voters. People like them. But a charismatic, popular candidate who looks like a winner will also naturally attract massive campaign donations from wealthy donors who want to back the winning horse.
The charisma is a confounding variable. It is pushing both the X and the Y up at the exact same time.
Therefore, our core assumption, the zero conditional mean assumption, almost certainly fails in this scenario. The unobserved factors charisma are highly correlated with our observable lever spending. We can confidently say that spending more relative to your rival is associated with getting more votes, but this simple regression cannot mathematically prove that simply dumping more money on a bad candidate will cause people to vote for them.
It is a vital distinction. Finding a mathematical relationship is not the same as finding the root cause. Okay, we've seen how the OLS machine processes messy data. We see its strengths and its blind spots. But what fascinates me is that while the data is chaotic, the machine itself is incredibly rigid. There are universal algebraic rules that this machine always follows, no matter what data we plug into it.
The word algebraic is key to understand here. These are not statistical assumptions about the real world. These are rigid properties that are mathematically guaranteed by the formulas of OLS itself. They are true by definition, regardless of whether your data is perfectly collected economic indicators or just random numbers you pulled out of a phone book.
The text lists three algebraic properties of OLS. Let's translate them. Number one, the sum of the OLS residuals is always exactly zero, which means the average of the residuals is zero.
Right. Think back to your rubber band analogy. The rigid wire snaps into a specific equilibrium. In that equilibrium state, the upward pull of the rubber bands above the wire must perfectly equal the downward pull of the rubber bands below the wire.
Exactly.
If they didn't balance out, the wire would still be moving. Therefore, the sum of the positive residuals and the negative residuals perfectly cancels out to zero. It's a mechanical guarantee.
Number two, the sample covariance between the regressors, the hex values, and the residuals is zero.
This is the machine forcing reality to match our theory. Remember the method of moments. We assume the population error was uncorrelated with X. OLS translates that into a mechanical mandate. It forces the calculated residuals, the U hats, to have exactly zero linear correlation with the independent variable in your specific sample. The line is drawn specifically to ensure this happens.
Number three, the regression line always passes perfectly through the sample averages. If you calculate the average X of all your dots and the average Y of all your dots, that exact coordinate will always sit perfectly on your OLS line.
It's the pivot point, the fulcrum of the seesaw. The line can tilt and angle itself to minimize the squared residuals, but it must always pivot around that exact center of mass.
These properties seem like great ways to check if your computer software is glitching. If you run a regression and the residuals don't average to zero, your software is broken. But understanding how the math cuts the data leads us to a much broader concept. It's a concept that sounds terrifying but is actually quite intuitive: variance decomposition.
It sounds like organic chemistry, but it's really just the mathematical process of slicing a pie.
Mm-hmm.
The pie represents the total mystery in our data. We call it the total sum of squares, or SST.
SST is the total variation of Y in our sample. It's a measure of how spread out our outcome is. Why do some CEOs make 500K and others make 5 million? Why are the soybean yields wildly different from plot to plot? Why aren't all the Y values just identical?
That spread, that variation, is the mystery we are trying to solve. And OLS takes that total pie of mystery and slices it cleanly into two pieces. The first slice is the explained sum of squares, the SSE. The second slice is the residual sum of squares, the SSR.
Total variation equals explained variation plus unexplained variation.
Yes, the SSE is the part of the mystery that is solved by our lever. It's the variation in Y that perfectly tracks with the variation in X along our regression line. The SSR is the part of the mystery that remains unsolved. It's the variation of the dots hovering away from the line. It's the dark matter still hiding in the U bucket.
Which brings us to a metric that anyone who has ever looked at an Excel spreadsheet or read a research paper has probably seen. R squared, the goodness of fit. The formula the text gives is R squared equals SSE divided by SST.
It is a simple ratio. It is the size of the explained slice divided by the size of the entire pie. It tells you what exact percentage of the total sample variation in Y is successfully explained by X. Because it's a percentage, it always falls between 0 and 1.
Right.
If you have a perfectly chaotic cloud of dots and your lever explains nothing, R squared is 0. If every single data point lines up perfectly on your regression line, SSR is 0, and R squared is exactly 1 or 100%, a perfect fit.
Everyone loves a high R squared. It feels like you've unlocked the secrets of the universe. But let's look at the actual R squared from the CEO salary example the text provided. The R squared for the model predicting salary based on return on equity is 0.0132. That's 1.3%.
That is correct.
I have to ask the obvious question. If 98.7% of the data is completely unexplained noise, shouldn't we just throw the entire model in the trash? We've explained barely 1% of the mystery. Why is a 1.3% explanation worth publishing in a textbook?
That is a very common reaction, especially from people who come from physics or chemistry backgrounds. If you are predicting the trajectory of a cannonball in a vacuum, you expect an R squared of 99.9%. But if we connect this to the bigger picture of the social sciences, the text strongly warns against worshiping the R squared.
Because humans aren't cannonballs.
Exactly. Humans are messy, irrational, and driven by 1,000 unseen forces. A low R-squared is incredibly common and almost expected when you are studying human behavior. The fact that a company's financial performance only explains 1.3% of the variation in CDO salaries isn't a failure of the math. It is a profound, accurate reflection of reality.
It means that 98.7% of why a CEO gets paid what they get paid has absolutely nothing to do with how well they run the company. It's driven by company size, their tenure, industry trends, how good their lawyer was during negotiations, or whether they play golf with the board of directors.
Yes. But, and this is the crucial part that redeems the model, a low R-squared does not mean the lever we found is fake or useless.
Hmm.
If our ceteris paribus assumption holds true, if we have accurately and cleanly estimated the specific relationship between ROE and salary without confounding variables, then proving that a 1% increase in ROE reliably bumps a CEO's salary by $18,500 is a highly valuable economic insight.
I see. Even if we haven't solved the entire million-piece puzzle of CEO compensation, we have accurately identified the size, shape, and color of one specific, true puzzle piece.
Exactly. A low R-squared just means our predictions for any specific individual CEO will have a massive margin of error. We can't use the model to guess Bob's salary accurately. But our estimate of the average effect of the lever across the entire market might still be completely spot on. We must not confuse the inability to predict the individual with the inability to understand the trend.
Okay, let's pivot to something that always trips me up when I'm looking at data. What if we change the way we measure those puzzle pieces? The text dedicates a section to the art of measurement and linearity. Let's say I'm looking at that CEO salary equation again. Salary equals 963.191 plus 18.501 times rho. The salary is measured in thousands. But what if I want to be pedantic? What if I want to present the data in exact single dollars? I multiply the y variable by 1,000. Does that break the machine?
Not at all. The algebra of OLS is incredibly accommodating to units of measurement. The rule is simple. If you multiply your dependent variable, y, by a constant c, the OLS intercept and the slope are simply multiplied by c as well. So if you multiply by 1,000, your new equation is exactly what you'd intuitively expect. Salary in dollars equals 963,191 plus 18,501 times rho. The physical line on the graph just stretches vertically, but the economic interpretation remains absolutely identical.
And what if I mess with the independent variable, the lever? What if instead of ROE as a whole percentage, like 10, I use the decimal equivalent, 0.10, I'm dividing x by 100?
The rule for x works inversely. If you divide x by c, the slope parameter is multiplied by c. Think about why. Your x units just got 100 times smaller, so a 1 unit change in x is now a massive leap. A 1 unit change from 0.1 to 1.0 is a 100 percentage point jump in ROE. Therefore, the effect on salary multiplies by 100. The new equation is salary in thousands equals 963.191 plus 1850.1 times rho decimal.
It scales perfectly, but notice the intercept didn't change. It stayed at 963.191.
Correct. Changing the units of x does not change the intercept because the intercept is the value when x is 0. 0% is the exact same thing as 0 decimal. The baseline doesn't move.
Okay, here is a pop quiz based on the text. If I change the units of salary from dollars to millions of dollars, and I change the ROE from percentages to decimals, does the R squared change? Does the goodness of fit get better or worse?
No. The R squared is completely immune to the units of measurement. It is a pure ratio. The percentage of variation explained doesn't change whether you are measuring that variation in pennies, dollars, pesos, or gold bars. The physical spread of the dots relative to the line remains proportionally identical. The pie is still sliced in the exact same ratio.
That is deeply reassuring. It means researchers can't manipulate their R squared just by changing scale. Now, let's tackle the second part of this measurement section, linearity. We've been harping on the name simple linear regression model. Lines are straight, rulers are straight. But anyone who has lived in the real world for 5 minutes knows that reality is almost never a straight line. Reality is full of curves, diminishing returns, compounding growth, exponential decay. How can a rigidly linear model handle a curved universe?
It does it through a beautiful piece of mathematical sleight of hand. When economists say linear regression, they mean the model is linear in the parameters, the beta 0 and beta 1. It means beta 1 is a constant multiplier, but, and this is the trick, it does not mean the actual variables, x and y, have to be fed into the machine in their raw straight line forms. We can mathematically transform the data before we give it to OLS.
And the most famous transformation, the absolute darling of economists everywhere, is the natural logarithm.
Logarithms are incredibly powerful. Let's go back to the wage and education example. The raw linear model said that every single year of education gave you a flat 54-cent raise. That implies your first year of elementary school gives you 54 cents an hour, and your final year, The grueling neurosurgery residency gives you exactly 54 cents an hour.
Which makes no sense. The real-world returns on education compound. The jump from a high school diploma to a college degree is much steeper than the jump from third grade to fourth grade.
Exactly. The raw data follows an exponential curve, bending upward. A straight line will do a terrible job fitting that curve. So instead of using the raw wage in dollars as our y, we take the natural log of the wage. We estimate an equation that looks like this. Log of wage equals beta 0 plus beta 1 times e duc. This is called a log level model because of the y is logged, but the x is at its raw level.
The text runs the data through this transformation, and the result is log of wage equals 0.584 plus 0.083 times ED. But wait, how do I interpret that 0.083? It's not 8 cents anymore.
No, it's a much more realistic interpretation. When the dependent variable is logged, the slope coefficient beta 1 no longer gives us a flat dollar amount. It gives us the proportionate change in y for a 1 unit change in x. To turn it into English, we just multiply the coefficient by 100 to get a percentage.
So 0.083 becomes 8.3%.
Yes. The model now says that 1 extra year of education yields a constant 8.3% increase in your wage. Because it's a percentage, the actual dollar amount grows exponentially as your base wage grows. An 8.3% raise on a $10 wage is 83 cents. An 8.3% raise on a $100 wage is $8.30. It perfectly models the compounding reality of the world.
So the underlying reality is a curve, but by taking the logarithm of the wages, we mathematically flattened the curve out so that our rigid OLS straight-line machine could solve it.
That's brilliant. It's a cheat code.
It is the most vital tool in applied economics. And we can go further. What if we log both sides of the equation? A log-log model. The text reruns the CEO salary example.
Yeah.
Instead of raw dollars and percentages, it compares log of salary versus log of sales. The computer spits out log of salary equals 4.822 plus 0.257 times log of sales.
When both variables are logged, the coefficient beta 1 becomes what economists call an elasticity.
Elasticity, that's a classic Econ 101 term. It measures responsiveness.
Precisely. In a log-log model, the coefficient means a 1% increase in x yields a beta 1% increase in y. It is a ratio of percentages. So here, the 0.257 means that a 1% increase in a company's sales is predicted to yield a 0.257% increase in the CEO's salary. It signifies constant elasticity. Whether the company makes $1 million or $1 billion, a 1% growth in sales always translates to a 0.25% bump in the boss's pay.
The naming conventions are simple, but you just have to memorize them. Level gives you raw numbers. Log level gives you a percentage change. Log gives you elasticity. As long as you know whether you fed the raw number or the logarithm into the slot, you know exactly how to translate the coefficient back into plain English.
It allows us to capture the profound nonlinear complexities of the real world while still using the incredibly fast, elegant math of ordinary least squares.
Okay, we have built the machine, we have tested it on real data, we have learned how to bend it to handle curves using logarithms. But we arrive now at the most critical part of the entire deep dive. We need to know the absolute non-negotiable rules required for this machine to actually tell us the truth about the population. Because right now, all we have is a mathematical calculator.
Yes, this is the transition from algebra to statistics. The algebra of OLS is dumb. It will always give you a line. You can feed it random lottery numbers on the y-axis and shoe sizes on the x-axis. It will happily draw a line, minimize the squared residuals, and confidently hand you a slope and an r-squared.
But the line will mean absolutely nothing. It won't point to any fundamental truth of the universe.
Precisely. To ensure that our sample estimates our little hats, beta 0 and beta 1, are actually pointing like a compass toward the true population parameters beta 0 and beta 1, we need a set of strict rules to hold. The text outlines the 4 foundational assumptions for simple linear regression, the 4 pillars of truth. If they hold, our estimators are considered unbiased.
Unbiased? That's a loaded word. What does it mean statistically?
It means that if we repeated our study 1,000 times, if we drew 1,000 different random samples from the population and calculated 1,000 different OLS lines, some lines would be too high, some too low. But if the estimators are unbiased, the exact average of all those 1,000 guesses will land perfectly, dead center, on the true population parameter. On average, the machine finds the true bullseye.
Let's run through these 4 pillars, because if one of them crumbles, the whole structure falls. RLS1, linearity and parameters.
This simply establishes the game we are playing. It demands that the true population model we are trying to uncover actually takes the form y equals beta 0 plus beta 1 times x plus u. As we just discussed, y and x can be logs or squares, but the unobserved beta parameters must be linear multipliers. We have to be using the right tool for the job.
RLS1 defines the game. Pillar 2, RLS2. Random sampling? We must have a random sample of size n drawn from the population.
This might be the most frequently violated assumption in the modern era of data. It ensures that the spreadsheet of data we are feeding into the computer actually represents the vast, unobservable population we care about.
Let's play a thought experiment to see why this fails. Let's say I want to find the relationship between age and physical fitness for the entire United States. I want a massive sample size, so I go to a high-end CrossFit gym in Los Angeles and I survey 10,000 people. I have a huge data set. I run the most elegant, perfectly coded OLS regression in the world on it.
And your results will be completely hopelessly biased. Because your sample is not random. You drew your data from a highly self-selected group of extreme athletes living in a specific geography. The older people in that gym are going to be phenomenally fit, totally skewing the relationship between age and fitness compared to the average American. The statistical properties of OLS completely collapse if the sample isn't randomly drawn. Size does not cure selection bias.
So RLS2 ensures we have fair players on the field. Pillar 3, RLS3. Sample variation in the explanatory variable. It states that not all values of X in the sample can be identical.
This isn't just a statistical rule. It is a hard mathematical limit. Remember the formula for the slope, beta 1 hat. The denominator at the bottom of the fraction is the sample variance of X. Variance is a measure of spread. If every single person in your sample has exactly 12 years of education, the spread is 0. The variance of X is 0.
And if you try to divide a fraction by 0, the math physically breaks. The universe implodes.
Exactly. You cannot draw a trend line if you only have one vertical stripe of dots.
Yeah.
How can you measure the effect of changing X if X never changes? You need contrast to see the picture. So RLS3 ensures game can physically happen.
And finally, the big one. The pillar that holds up the sky. RLS4. Zero conditional mean. The expected value of the error given any X is 0.
We spent a lot of time wrestling with this earlier, but it cannot be overstated. It is the bedrock of causality. The unobservable factors in the background cannot be systematically related to our explanatory lever. The U bucket must be balanced across all slices of X. RLS4 ensures the referees of our game aren't blind, so to speak. If all 4 of these pillars stand strong, OLS isn't just a math trick. It is a truth-seeking missile.
Okay, let's step back and look at the entire landscape we've unpacked today. We started with the goal of finding a way to extract real, definitive insight from an overwhelming sea of chaotic data. We wanted an X-ray machine for the economy. And what we found in the simple linear regression model is that it isn't just a mathematical equation to be memorized for a test. It is a philosophical lens.
It is a formalized way of thinking about the world.
It is a way to try and isolate variables in a noisy universe. It forces us to acknowledge our own ignorance by physically writing it into the equation as the U bucket. And most importantly, it forces us to be incredibly explicit, mathematically explicit, about our assumptions. It demands that we prove our ignorance isn't secretly pulling the strings and biasing our data.
It is a deeply humbling tool. It forces the researchers to acknowledge exactly what they do not know, and it strictly limits the sweeping claims they can make. But when used correctly, when the user respects the limits of the data and ensures the 4 pillars are intact, it is arguably the most powerful analytical tool humanity has developed for understanding complex relationships and observational data.
It really is. It translates the chaos into something we can read. Now, before we sign off, I want to pose one final thought, a speculation that extends beyond the textbook. We spent this entire deep dive obsessing over the error term, the U bucket, the unobservables, innate ability, soil quality, the charisma of a politician, the ambient humidity in a kitchen. But think about the era we are moving into right now. We are entering an era of absolute, unprecedented data collection.
The bucket of unobservables is rapidly shrinking.
Exactly. Our phones track our heart rate, our exact eye movements, our location down to the centimeter, our browsing habits, the exact tone of our voice during a phone call. Agricultural drones map the mineral content of every square inch of soil.
The U is becoming X.
So what happens to the social sciences and, frankly, what happens to human free will when the bucket of U finally becomes completely empty? What happens when we can measure the exact neurochemical state of the farmer, the microscopic genetic potential of every student, the exact algorithmic exposure of every voter? When there are no unobserved factors left, will these linear models perfectly deterministically predict human behavior? Or will the mathematical models break entirely because the mystery, the random noise of the U bucket, was actually the only thing giving the system room to breathe?
That is a chilling and incredibly profound question. Does perfect data lead to perfect models of humanity? Or does the sheer complexity of a fully observed human system defy even total mathematical modeling? If there is no U left to act as a buffer, the very nature of cause and effect might look completely different than a straight line.
It's something to chew on. The next time you are scrolling through the news and you see a bold headline claiming, "New study proves pulling this lever causes this outcome," you now have the tools to look past the headline, look at their data, look at the line they drew, and ask yourself the most important question in econometrics. I wonder what's hiding in their yeets.
Thank you for joining us on this deep dive. Until next time, keep questioning the X-rays.